Good morning, everybody. My name is Sailen Tripathi. I lead the file system development work in Intelliflash division of the Western Digital. This is the product which came from acquisition of PCle. It's basically an all-flash array both on SAS and NVMe. I'm going to talk about relevance of some of the techniques which we have been using in data redundancy or drive availability when there is a failure, and see if they are relevant going down the line also. So I'm just going to take a peek at how the flash capacities are increasing over a period of time, starting last 4-5 years, and how it's going to look in next 4-5 years. How much is the performance characteristic changing on that? Because these are very critical aspects when you're deciding what are the techniques you're going to use for the redundancy purposes. And then I will describe, based upon those inputs and what we see as a viable option, one of the viable options for the resilvering mechanism going on the line. Capacities are increasing even in TLC. Even if I discount QLC capacities, TLC itself right now shipping most common model is 8 terabyte, 16 terabyte is already out in SAS in both NVMe, and by the end of the year, 32 terabyte, 31 terabyte will be available, and maybe next year it will be 60 terabyte. So it's going to come even in TLC, and when QLC comes, the capacities will double naturally over a period of time. So from flash capacity per drive or whatever is the unit, it's increasing over a period of time, going down the line even next 4-5 years, and it will be pretty significant. Just taking numbers, only two numbers I'm interested here. One is sequential read and sequential write, because those are the two critical numbers, and of course random numbers give some idea. This is a NVMe drive spec, which is you can do 800K random IOPS at 4 kilobyte. So if I do rough math, if I just do random IOPS, it's going to be a different performance number, but sequential read and write are pretty significant. They're like 3 GB versus 2 GB, and if you do sequential, it's a different world. And almost similar, lower number on QLC side, but pretty similar numbers are expected. One of this is an Intel drive, 1.5 or close to 2 GB per second for read and write. One noticeable thing is that in these things, the read numbers are far more higher than writes, and both in random and sequential, and it will be worth exploitable in any of the design. If you can leverage that, will be a good advantage. So these are the observation in summary. Increasingly dense capacity per rack unit over a period of time, and that's given from the trend of the drive or underlying media which are coming. QLC will be coming pretty soon. It's already there. It will be mainstream in a couple of years. TLC is not going to disappear, but it will also increase in capacities. There is a very likelihood QLC may start replacing some of the SSDs. May have a long tail, but still it will start appearing in several use cases where read is far more prevalent requirement than writes. If writes or sequential writes are prevalent, SSDs will still be there due to higher capacity and lower cost. But one thing, even though these capacities are increasing, the annual failure rate is not trending down. That it's almost similar level. It's not going down, and it's true for Uber rate also. So bit error rate from the drives, uncorrectable bit error rate is also steady, which means with increased capacity with the same rate, that means the reliability of the drive or the time which is available with the drives is going down, trending down. And another factor of this capacity is the higher the capacity, the blast radius is even higher. So the impact of that capacity, how much data it's going to impact, it's increasingly getting higher and higher. One drive failure of say 16 terabyte drive, and if you're using all your application, almost every application may be impacted. So overall, the observation is that fast resilvering is going to be a pretty significant differentiator in pretty significant differentiator in all those solutions where these kind of capacities are being used, because the lower the time in resilvering, the impact on the end system is going to be much lower, and that will be end-to-end realizable thing. Another thing for these things, main purpose of these drives whenever they are being right now used is latency. So if Resilver is running, the critical factor they're always driven is that latencies should be significantly similar when there's no failure. So that's a extremely critical requirement. Customers can see in the profiles in the analytics chart that the latency before and after is pretty significant, and it impacts big time. So that is going to be a challenge to solve also. So just taking a look at some of the numbers with it, as I said, random, if you do it, the drive says 825K, you can do at 4K. So you can do one read, if everything is random, only 303 megabyte per second. But it changes very dramatically, and the next two numbers are what we have observed, not what the drive publishes, which is the drive says 3.2 GB per second. But even if I do completely random at 128 kilobyte, it immediately goes 3 times. And if I do sequential, a realizable number running on our software stack, we can see the same drive can do 2 GB per second sequential read, which is it's a huge difference between 330 to 2 GB. So time-wise, if I see it is basically there's a significant, an order of magnitude difference between choosing a random and sequential if you're looking for just a read purpose. And this is basically crux when you're trying to resilver, because you have to read from the rest of the system, rest of the drives, and populate. That's why this number becomes very, very critical, and that's why I'm laying the factor here, and some estimate how much time you need to potentially, let's say, right side is free. I'm just bound by the read, so the difference is between 2 hours to 15 hours just by choosing one side to another, which implicitly implies if you do sequentials, for your resilvering is always good, and of course if you do on higher sizes, even if you do random sequential is good, but don't do random, don't do small IOs. That's kind of key insight into that. So I'm just going to take a look of some of the choices which we had, and how much impact it does when there's a failure and all that. It's mainly a qualitative analysis, not exact, but comparison will give an insight how much impact it may have. So let's say there's a mirror or one replica. It could be also a 2 copies model, which you have in some of the system. The biggest problem in that model is that the impact on the surviving drive is unpredictable if it is to drive, because IOs on the existing drive is not going to stop. You are going to read from that, and there's a client IO which is coming, and there's a very high chance the client IOs get crowded out, or at least they are very significantly impacted by the latency. So RAID mirror, for those kind of capacity, if it is going to take a longer time, it's not going to be very, very useful. This is in addition to wasting capacities on top of that. So basically, to maintain the latencies and all that, you have to throttle some of the background operation, in this case the resilvering, so that client IOs are not affected, but that has a reverse impact. It's going to increase the resilver time, which means the time window in which your client IOs are impacted is going to be higher and higher. So it's not going to be very useful with higher capacity. Second, you can have a triple mirror or 2 replica. It's like equivalent to 3 copy model or whatever you have. Similar problem, slightly less. The client, because you have more spindles now, more drives involved in it, so maybe IO impact is roughly divided between the 2 surviving copies of drives. But it still may crowd out because you're running 1/3 less resources, and if you're really read bound, it's going to create a significant latency. Not only read bound, if you're writing, read and write combination also lowers little of the performance, especially the latency gets higher. Slightly better than that, but significantly higher wastage. So this one doesn't look like very good model. So I'm going to rate first and Erasure Coding from this particular purpose. Both of them are similar. I'm just going to say what it implies. So from previous to what we saw, that from client latency purpose, number of drives matter a lot when there's a failed drive, because the higher the number of drives, you can amortize the IOs which you're doing for both background operations over number of drives. So the impact is far more manageable than when you have 1 or 2 drives to spare for. So that is a good property if you go Erasure Coding model. And the underlying reason is that number of drives participating in Erasure Coding sets is much higher, 15 to 23 drives, or depending upon whatever you want to choose. So that gives slightly more manageable client IO latency perspective, and of course, even the space wastage is known. But if the drives are on the network, it has a significantly different bottleneck, which is network performance, not only for write performance, but also for read and getting the data from others. It impacts latency even higher if it is not a very closed network system. So if you're probably running in a rack with the very good switches and all that, it may have little impact, or it will have some impact, but manageable. But the moment networking gets involved, it's somewhat unpredictable latency. Write latency is well known. I don't need to describe why Erasure Coding has some impact on the write latency. As I said, it's manageable if it's not across network. Computational overhead is, of course, much higher than whatever model we discussed, both mirror and this one. You need to do far more complex computation before you get the data.
Can you please explain what you mean by amortized IO?
So basically, there are 2 IOs right now coming in a system when there's a failed drive. One is the client IO reads which are coming, and also the IOs which you are generating to resilver the failed drive. So you're reading the old data from existing drives and client, but since the number of drives in the set is higher, so read which you require is distributed. So instead of 1 or 2 drives, it's like 10, 20 drives participating. So it's like 1 by 10 or 1 by 20 load additional going for read purpose for the resilver IO. So it's an order of magnitude lower than, say, replica model or copy model. And as I said, because there's a computational overhead and write latency, there is still maybe a requirement for throttling, especially for the background operation, in this case, resilvering. So not as bad, but it still depends on where it is being used. If it is a closed network, good networking, it may be a reasonable choice versus a space trade-off. Now, even if you choose reasonably good codes, it's still you're looking at 1.33x times the space wastage compared to some of the other schemes. So, but not a bad choice because of the number of drives involved. Now, looking at the RAID, single parity or triple parity, how much it plays from drive perspective is similar. Double parity and triple parity, you can put almost similar number of drives as you have in RAID Erasure set. So similar benefit you get what you have in Erasure Coding. Write latency is also amortized because you can, again, you're slicing the writes across the devices, so you can control how much you're sending, so it still works okay. Network latency is if your underlying drives are directly connected to the system, then you're not going on network, you're going on PCI lane, and in general, say, Skylake, you have 48 lanes, even if you're connecting dual lanes, so 24 drive or 6, it's significantly higher bandwidth available for you from the drives in reasonable system. And for 4 drives, potentially you'll need 100 gig card, but in this you can have 24 drives and it works fine. Again, computationally, I'm just comparing it from Erasure Coding, slightly better, but not very significantly different, especially if you use SIL libraries and all that from Intel. It's far more manageable, especially the latency side. So RAID also is, again, a choice for you, it's a space and complexity trade-off. It's slightly more complex than copy models. You have to, it's a math computation you need to do, and there are several cases computational permutation involved when you're rebuilding the drives. But one key insight from Erasure Coding and RAID is that number of units which involve, if it is higher, it's going to be better. But there's additional impact, which is completely orthogonal to this. The more number of drives you involve in a set, the blast radius is even higher. So the two contradictory things are working in a play. So you need to optimize number of units in one dimension, but also you need to watch for how much is the blast radius. So it's like some trade-off in between which you need to choose. You cannot have a system where, let's say, you do 100 drive, and if it impacts, probably resilvering impact is much low, but it has much higher impact on the applications which are mapped onto that system. This is what I was saying, and drives are better, whatever you do. And second thing, as I saw the specs of QLC and TLC drive, delta between read and write, both in random and sequential write, is good. So if you can get a model where you can exploit that additional delta of the read while you're doing that purpose, it will be far more beneficial. And it will, what it implies is that, let's say I'm doing same number of writes and same number of reads, because there's additional read, I can absorb slightly additional, more additional read than write. So that is an advantage if it can be leveraged nicely underneath. Computational hover, always you want lower the better. And another critical factor is in these drives, you don't want to resilver the things which you truly don't you are not using. So if it is 16 terabyte drive, you don't want to waste your time if it is just 50% used. There's no point doing that work at low level, because it's just going to, you will be forced to do that work without any real useful yield. And this was already discussed. The sequential writes, higher I/O, they are much better. Even if it is random sequential, is slightly better. So based upon these insights, I'm just going to describe what model we have implemented in our system, and what some analysis how we see that it will be still very useful for next few years based upon the model which we have chosen. So this is a typical block diagram of our appliance. It's a two-node system, 24 drive shared between those two controllers for high availability. And drives are connected through 48 lanes, two PCI lanes. So effectively it's 24 into 2 for each from both the sides. And what we did in the underlying software is that we delink the client I/O from the device I/O. So whatever client I/O is doing is small, big, we don't care. At the device level, every I/O is always done in big I/O. So, for example, anything you do at the device is a stream of 1 megabyte chunk, or that the size is configurable. You can choose some chunk size, and client I/Os are mapped onto it. And it gives nice other properties that with number of cores you can do everything concurrent as you have other things. So this segmentation allows us to spread the work in the file system itself in fairly parallel way, concurrent way. And and all the small chunks, they are mapped in that chunk in a chunk map header, which is maintained outside of it. So just to give the context how the data is laid out, and I'm going to talk how we then do the resilvering process. Yeah, go ahead.
So is the chunk always fixed to 1 megabyte?
No, we chose 1 megabyte chunks for a purpose. In our given set, we wanted to, as I said, I was looking something which gives me 128 kilobyte per drive. So we typically use 8+2 or 10+2 in our combination when we create a set. 1 megabyte is mainly derived of that. If it is slightly more, it's configurable. You can choose whatever you want. Anything higher than 1 megabyte, I will say is better. 1 megabyte, 2 byte. But there's additional factors involved, latency. That's why we chose 1 megabyte. So, for example, the column which is affected or failed, when the read comes on that particular column, you need to build that whole chunk before you can send out the read request. So the higher the size, the latency for that particular IO will be higher. And even though it is flash, whatever latency you see for 4 kilobyte or 32 kilobyte, it will be far higher for 1 megabyte, 2 megabyte, 4 megabyte. So the second pull, why we chose 1 megabyte is like chose the minimum possible and still get the best sequential performance. And 1 megabyte kind of fits it, but 2 megabyte or 4 megabyte also will not be as bad. So how do we do it at the device level? Everything, since I said everything is just a chunk. Now that has a very good property. I can spawn this chunk resilvering or whatever you say to as many number of threads, as many number of cores, whatever is underlying system, and they all can fetch from the underlying media, and then they start the process for each chunk independently. So there's no dependency on anything, and it's fully sequential. Headers contain in-use data map, basically what, as I said, small IOs are mapped into some of the headers. So if there's a free, they are also recorded in those header maps in some way that this is in use and not use. I'm going to describe why it's useful for us as another trick which you use to utilize even more bandwidth of the drive, but just for time, hold on to it. We do data and metadata separation at the lower level for obvious purposes. It helps in doing the meta in slightly higher prioritization, because lots of read IOs are dependent upon the meta, so it reduces the overall latency. Again, read and writes are generated in higher size, then they are sorted at the device generation level, and then it generates a stream of read requests when I'm doing the resilvering. So it pretty nicely creates a random sequential pattern on almost all the drives. Same thing for the writes, they're always done sequentially, sorted and all that. So again, random sequential pattern on the drives. So just to give an example, for 2 GB per second for net read per drive write is read is just 200 megabytes per second. So as I said, the read capacity is 3 GB per second per drive. If I am doing 2 GB per second resilvering also, the additional read impact on the drive is just 200. So it's less than 10% or 5%. So the impact on the client latency because of this additional read can be absorbed much nicely. So that gives a very good bandwidth. But one thing, what I didn't mention here is that even when I'm reading from every drive, the write is still going in the fail drive. So all the write for resilvering purposes is still reaching that fail drive, which means whatever is the bandwidth of that particular drive is going to be the real factor deciding how much time it will take to resilver that set. So that that can also be optimized by, we don't need to create the write just going to one drive. In our model, we can nicely distribute the writes also, which is induced by the resilvering across all the drives. And if I can do that, then I can completely control how much read and write impact it's causing on every drive based upon that. And I can leverage more bandwidth out of the system. So this is what I was mentioning. We maintain in-use map in the chunk map headers, and that we use for this purpose. So what we do is we use kind of intelligent use of the garbage collection process or recompaction process and combination of resilvering to get a model where I can leverage more number of underlying media in the writes. So let me take an example. Let's say I have a chunk which I know is just 10% or 20% used, remaining is free. So instead of resilvering that particular chunk, I just do a fresh rewrite or recompact that chunk along with other chunks. So what it does that I don't need to resilver that 1 megabyte chunk, and when I write 1 megabyte or whatever chunk, whatever is still in use, combine it with the other chunks, the write gets automatically spread to every drive. So I am resilvering also the old data. At the same time, I'm moving to different locations. What that gives me, that I can nicely send that resilvered write also to more than one drive in practice. So that gives a very nice property that I can sustain latency for all the drives in very nice way. So read I can manage. So as I said, it's a combination of rewrite chunks and resolver. We get a heuristic on basically based upon the underlying media capabilities. We decide at runtime how much I can queue to an underlying device for write purposes for a resolver, and how much is for recompaction. And that matrix decide what we will recompact and what we will resilver. So as I said, we can choose that matrix based upon how much is the client I/O, and it's dynamic adaptable. After every I/O, we can determine whether one of them is going to impact the latency of the client side, so we can reduce one or other to maintain that purpose. As I said, dynamically adaptable to exploit the bandwidth. As the additional bandwidth is available, it's given to the recompaction or resilvering, and it shares the read and write on all the drives involved in that. So it provides the least impact, both in terms of bandwidth and latency. So now this is true for today. Let's say this is 8 terabyte, 16 terabyte drives I'm talking about, which means I didn't mention the time, but time is pretty much, I mentioned in the first drive, you can do 2 GB per second resilver. So pretty much within 7 to 8 hours, you can resilver any number of 16 terabyte drive. How is going to be when PCI speeds will double? So starting early next year, PCI Gen 4 systems will be available, which means the drive bandwidth also is doubling. So from 3.2 GB per second, 7.5 GB per second for read, and write also will be close to 4 GB per second. So even the capacity is doubling in, say, 30 terabyte or 64 terabyte in the same window, even the bandwidths are increasing at the underlying level, which means if I follow the same pattern, read and write, even for increased capacity, I will be able to maintain the same time for increased capacity also. So for 30 terabyte with Gen 4, it will have same time as we have for Gen 3, 16 terabyte. And if I have, say, 64 terabyte at Gen 4, Gen 5, it will be same time. And this is pretty much next couple of years, 2, 3, 4 years down the line, this will be model. And underlying media performance, and this has a double impact because PCI lanes are also increasing, plus PCI speeds are increasing, and same thing will also happen at the drive. So it's net end to end, it will have a bubble up impact. So both read and write will almost follow the capacity trend for at least next 3 to 4 years. So whatever is sustainable in time perspective is equally possible to have that similar sustainable time in next few years also. But there's additional things happening. I mean, blast radius thing which we talked. Capacity, the time is one factor which we already discussed. Even if it takes same time, but if you have a 30 terabyte drive and if your one die has failed or two drive has failed, what we're trying to find out, is there a way to localize that particular drive failure instead of failing the whole drive? So one chip might have failed, even if it is one gig chip or whatever. Your capacity loss may be just few percent, and your resilvering data may be very, very small instead of just failing the whole 30 terabyte or 64 terabyte. And this is why we have been pushing to get things like endurance groups, which allow you to isolate the failures from the top until the die level or channel level. So there will be some cases where everything fails. Of course, it cannot be get rid of it, but if it is part failure, die failure, something which can still allow rest of the subsystem to survive, the endurance groups, if they're equally, if they are done right, then it will make set of these drives appear as if there are multiple drives packaged in one drive. So even if it is 30 terabyte drive, 1 terabyte unit might have failed, but remaining is still survive. So there will be additional way to handle the blast radius in this model, where we can just localize that particular failure to that die instead of doing resilvering. And this chunk model works very nicely with it, because we can, from the application itself, we can immediately map which particular endurance group belongs to that chunk group, and then I can just go ahead and resilver only that chunk group instead of doing everything. So it will localize the work required even less. Still work in progress, but I hope that in the next couple of years it will definitely come to fruition and we'll be able to exploit. Similar zone namespaces and the endurance group, they are also, in a way, they will localize performance impact not only to the unit by endurance. You can also map it to an application. So if an application is end-to-end mapped from user level to an endurance group or a zone namespace at the lower level, I can localize the impact on that particular application itself. Instead of every application being impacted when there's a drive failure, you can just have one application impacted, and then you can use other techniques. You can move that application to the drives which are surviving well, or you can have other techniques which will help you, but at least it provides you a way that you can localize the performance impact through other mechanisms. And the chunk model fits very nicely in that you can map those tags, localize those tags or localize those chunks which are impacted by it, and you can just spawn resilvering only on those chunks instead of going and touch everything in any other model. So there's one thing I did not mention in all this. So what it implies that using Erasure coding, if it is not network bound or RAID-G, it's going to be a really viable option even in next 3-4 years, despite increasing capacity. One thing I did not mention, it doesn't consider the availability in the picture, because the system where we are using, the system itself is available, which is there are 2 nodes, and if one node fails, that other node takes over the drive, and drives are shared. If there is additional requirement that you need to make it available when there's a node failure also, some of these conversations will be different. For example, if I have 3, 4 nodes, 5 nodes, 6 nodes, and they don't have a shared drive, you don't have any option. You have to go to network. So there's no choice. Network will be involved in that. So in that case, RAID-Z on RAID double parity or Erasure coding, it will be evaluation based upon how much impact it causes because of network and competition. And third factor, major factor, will be how much space overhead you are willing to give away. So just comparing the Erasure coding on our system, if I do triple parity RAID and Erasure coding, actually with fail drive, the Erasure coding performs better than the triple parity, just by exploiting some of the Intel instruction sets and other things, and also the way it can put the data more in random sequential fashion than triple parity RAID. So our conclusion is that RAID parity, RAID model, and they will be efficient, and you'll be able to use either Erasure coding or RAID in all-flash high performance systems also, at least in near foreseeable future. If you have availability option also needed from that, Erasure coding works much better. But even then, the recommendation will be that you do some sort of RAID first, because you don't want to do the node level rebuild when there's just one die failure or one rebuild, one unit failure. Because networking is still going to be slightly lesser than the PCI bandwidth which you will have available in your system. So, in summary, whenever you have that kind of set, more units will help, and increasingly new trends in NVMe space in terms of zone namespacing and endurance groups ideas which are coming, they will help localize some of the blast radius issues which we have to contain the performance. And then it will be a matter of space and performance trade-off to choose either Erasure Coding or RAID-G. Right now, our most preferred model is double parity RAID. And if somebody is looking for triple or more than 2 or 3 failures, that's when they will start going and look at Erasure Coding systems. Thank you.